My name is Brianna Olson, and this is my CPU final project for ECEN 160. The first part of the CPU is the counter. This increments through the machine code instructions located in the program prom. Each location in the program prom holds one 16-bit line of machine code. Bits 0 to 3 can either hold data, or 0 to 2 hold the address B for the register. Bits 4 to 6 go to the register as read address A, bits 8 to 10 go to the register as the write address D, and bits 12 to 15 go to the instruction opcode prom. The instruction decoder configures these control signals to execute the instructions. Bit 0 is the write enable for the register, bit 1 is the write enable for the ASCII display, bits 2 and 3 are selector bits for the MUX, bits 4, 5, and 6 are selector bits for the ALU. The instructions in the prom are programmed to either do nothing, load, move, display, exclusive or, and, add, or hardware subtract. The fourth part of the CPU is the register input data multiplexer. It can take 4 data bits from either the program prom, the ALU, or output A of the register file, and determines which of these 3 to send to the register. The fifth part of the CPU is the 3-port register file, which consists of a decoder, a register file, and 2 8-to-1 multiplexers. The decoder chooses which register to write to using the address input and enable. Each 4-bit register is made of 4 1-bit registers that each contain a single bit of data controlled by a 2-to-1 MUX and a D flip-flop. The register files connect to 2 8-to-1 multiplexers that hold this data to be read determined by either address A or B. The sixth part of the CPU is the ALU. The ALU takes the 2 outputs of A and B from the register files and performs a function on the data determined by the sub and AFS lines from the decoder prom. The ALU can perform an exclusive OR, AND, or add. The adder is made of 4 1-bit full adders. The ALU can also perform a hardware subtract using the subline and the adder. The last part of the CPU is the ASCII display, which displays information stored in the register files as programmed to do so by the machine code in the program prom. Here are testing phases 1 and 2 being run by the CPU. The software subtract was done with the ALU by first changing 3 to its 2's complement by adding 15 to 3, which creates the inverse of 3, and then adding 1. This was then added to 4 to get 1. The hardware subtract was implemented by adding the sub input line and 4 exclusive OR gates to the ALU. Because of these gates, when sub is 1, then B will be inverted. The sub 1 will then go into the adder as a carry in to get the 2's complement of B. In this case, 4 and the 2's complement of 3 are then added together to get 1.